Hello, everybody. My name is Thomas Gruber. Today I'm giving a talk with my colleague Georg Hager. We both work here for the NHR at FAU. I'm originally a software developer, but I'm using Slurm from time to time. And I'm digging into the more complex stuff when it comes to Slurm. So today we are talking about best practices and some advanced usage if you need have some special workflow or special case. Okay, we start with the Slurm basics. Unfortunately, I cannot remove that on top. I don't know. I should just ignore the line. So, of course, a good starting point is always to point to our documentation. We try to put a lot of work into the documentation so that it's up to date and you find all the information that you need. In the documentation, we have some general one, which is basically doc.nhr.fau.de. There's, of course, a Slurm-specific page below it, and we have a cluster-specific page for each of the clusters. There's a page which explains a little bit what is the specialty when it comes to Slurm on this machine. Then there are, of course, the official Slurm documentation. So there's a man page or the documentation page for each of the Slurm commands, so srun, sbatch, sq, and how they are all called. Most of the information there is much better or more condensed than on our web pages, but of course they have to cover all the different versions and so on. For people coming from other computing centers that use like PBS or LSF or the other batch schedulers, there's a Rosetta PDF, so the second one on the lower one, which basically tells you how the commands can be translated from like PBS to Slurm, so it makes it easy to change computing centers. And there are, of course, whole tutorials about Slurm. So if you have a specific workflow, it might be documented there, and they describe how they think you should do it. Okay. Then we start with some terminology that we are all on the same page. So a job is an allocation of resources and to a user, and he can use it to run any compute for a specific amount of time. A partition is a set of nodes. Like in most systems, you would think like it's a cluster, but a partition is just a part of the cluster. And these machines all have a special property, like same hardware architecture or same GPU type, or so on. There can be constraints put on each partition when it comes to job size, maximum job runtime, who is allowed to use it, and stuff like that. In our case, we mostly call it queues in our documentation and so on. We call it queues because that's what's in the end happening there. A task is how many instances of your job are executed. So if you have an array job, for example, you have like multiple tasks below one job, and a task. In Slurm, a task is completely different. Sorry, a task in Slurm is like an MPI process. Whatever in normal MPI world, you call it them MPI processes. In the Slurm world, that's a task. So you start multiple tasks for one MPI application. Then a job step is like if you call multiple times srun or multiple times MPI exec or something like that, each of these will be counted as one step. So one step in your job where you use the resources that are allocated for you. QoS or quality of service, it's a limit on a per group basis about like the quality of service you get. We could say like this group only gets the good nodes or the bad nodes, what we don't have, but this would be one of those things, what a quality of service means, or only the nodes which have a CPU frequency above 3 gigahertz, for example, because we want to be fast, and then Slurm selects the right nodes which fulfill this quality of service agreement and schedule your job there. GRES is a generic resource. In our cases, we just have one generic resource, and that's the GPUs. There are other centers which provide other global generic resources as well. So like an FPGA, for example, can be seen as a general resource and stuff like that. And a CPU, so Slurm uses the term CPU, which is like very ambiguous nowadays because a CPU has different meaning depending who you ask. In Slurm, a CPU is equivalent to a hyperthread, so the lowest processing unit a chip has. In most cases, it's like a hyperthread if you have SMT enabled. In our center, most systems do not have SMT, so it's the same thing like a core, CPU core. So I call them hardware threads because that's more specific than a CPU. A CPU is the whole thing you put in a PC with multiple hardware threads and so on. So yeah, it's a different terminology when it comes to Slurm. Okay, so let's go and look at the first batch script we have. One of the main things you always should do in your batch script is start with bin bash -l, so that you get a login shell. This is very important in our center, otherwise you don't get like specific environment settings set. So if you want to use modules and didn't use -l, it will tell you module command not found. That's simple, yeah? So the module command is configured in the environment. If you don't specify -l, the module command is not there. So this is a easy thing. If you see module command not found in the output of your scripts, you probably have forgotten the -l. Yeah, and then there come the whole resource utilization, resource specification, and then our script. I just go through the same script now line by or almost line by line to see what we see here. So -l, very important. Then there's if you work on the front end and define some environment variables, loaded modules there and so on, and then you start a job, the whole environment from the front end will be taken into the job. So all your loaded modules and so on. And if you have loaded like the Intel compiler on the front end and then just start a batch script which wants to load a different Intel compiler, you get a module load conflict because you try to load the same compiler twice at different versions and so on. So this is getting problematic. And if you don't want that, and that's what we recommend is to do this -- export equals to none. This means nothing is pushed from the front end to the compute node. You have a clean environment as soon as this line is done. Yeah, so basic environment you get. But on the other hand, inside your batch script, you want that things are forwarded to the subshells. So if you do an srun, you want that the command you execute also sees like the modules you loaded. Yeah, that's why you need this unset slurm export env line again, because otherwise it would not give your modules back to the srun command. So srun wouldn't know that there are any modules loaded, any environment variables set, and so on. So these two lines always should be combined. You don't need the empty line here. This is just, we have it in our documentation. I copy pasted it. But in the end, you can directly put them together. There's another command which does basically the same thing, but this unset is much more handy. If you want to specify where the output should be written and also the error of a job, you can do that in Slurm with -- output and -- error, and then some file specification. We do not recommend you to do that because it's very error prone. You overwrite the same file in the folder. Yeah, if you run the job twice in the same folder, it will overwrite your files. You do not want that. So if you need that, please use some file name patterns that Slurm provides. So like a %J is replaced with the job ID, %X with the job name, and so on. So you can create basically the output file based on the inputs of your job. So very handy. And if you do that, then the problem of overwriting your own files is minimalized, because the job ID, if it's in the name, it will probably not be happening again in the next year or 2 or 3 that you see the same job ID again. Officially never, but it will come back. Yeah, so this fits for output in -- error. Here's a link to the patterns from that Slurm provides in the official documentation. I didn't want to type them down, just as an example. Then since some time, we have configured our systems to use the power-safe CPU governor, which means like it tries to reduce the power consumption of the node, especially in idle phases. But the problem is that ramping up the performance or the frequency is much slower than you would expect. And even sometimes you do not even reach the highest performance of a node, simply because the power-safe governor says, yeah, you're burning too much energy. I limit you now to the base frequency, for example. So if you want to have the highest performance, add this line, CPU frequency equals high to high column performance, which means give me the high performance, a high frequency. You have the choice to choose between the high frequency and the high frequency, so only the high frequency, and use the performance governor instead of power save. That's basically this line. Very important is it is not enforced by the sbatch command. This CPU frequency is enforced by the srun command. So you have to use srun if you want to use the CPU frequency setting. Otherwise, it will simply not apply the CPU frequency. Yeah, so always use it in combination, the CPU frag on top and the srun for the actual command. A big problem is affinity control. So in order to get the highest performance and less performance variation and so on, it's crucial to pin your application to specific CPU cores, either the MPI application or then the OMP threads or threading solution things. And for that, you need to tell Slurm what to do or to tell the runtimes what to do. And for hybrid jobs, so for normal jobs, MPI, it's just minus n tasks. So how many tasks do you want? The CPUs per task equals 1 is then implied automatically. If you want to use hybrid jobs, so MPI plus OpenMP, for example, you have to set the CPUs per task to tell the MPI runtime or Slurm, basically, I want to have like 4 CPU cores so that I can schedule the OMP threads there. Me and a student assistant, we have tested a lot around on, at least on Fritz, for hybrid and MPI only jobs and try to come up with a general recommendation which works in, let's say, 99.8% of the cases. So it's not the do not copy this block blindly, yeah, but it is a good recommendation to start with. And we basically tell Slurm to bind the tasks to cores. And we tell that the OpenMP runtime that it should use the same amount of CPU cores as you have specified with CPUs per task. It should bind the cores and it should use cores for that. There's a question?
I don't know if I made something wrong, but on Fritz, in my tests, per default, affinity was disabled for S1, for Slurm. So when you just run a job, the processes were like arbitrarily.
Yeah, exactly. Yeah. And this does not happen if you set the CPU Slurm minus CPU bind.
But I wonder, because previously, for example, with Intel MPI, the startup mechanisms would always enforce some kind of affinity.
Yeah, but not with Slurm, because Slurm is more clever than anybody else.
That's a good question. The question is, if you start an Intel MPI binary with Slurm, with srun, who's responsible for the binding? If Intel MPI has a default binding, it should still work, but it doesn't unless you do it like that.
Yeah.
For some reason, maybe they changed something.
The Intel MPI runtime.
You have to tell Slurm what the default is, and obviously at our side, the default is low pay.
Yeah, exactly. And even the Intel MPI runtime will ask Slurm about its settings to use. So even if you use MPI exec from Intel MPI, it will ask Slurm what is the setting and will apply those.
And why not use the MPI-specific startup mechanisms?
Because they interfere with how Slurm wants to do it.
But you could still do it. Yeah.
You could still do it. So I have you do not use. It's basically do not. We are not recommending it. That's the basic better word. And if you want to do that, specify minus CPU bind none. So you hand over the binding mechanism to the actual MPI implementation, and Slurm doesn't interfere with that. That unfortunately doesn't mean that Slurm doesn't apply anything. In some cases, Slurm overrides this and tries to be clever. Nothing to do there. That's Slurm. If you want to do a hybrid with Intel MPI, we recommend these settings. So Intel MPI pin domain OMP, which basically asks the OpenMP runtime, how many threads do you want, where do you want to place them, and I'm putting my MPI tasks around it. And you want to have a compact ordering. If you want to do hybrid with OpenMPI, use bind to cores and map by in this more complex statement here, which basically tells split the node into parts of OpenMP threads and then take like the amount of processes you want. you probably get better performance with this one. It might not be the optimal performance, because for that you should know how your own application works and how the affinity should be set. But it's better than nothing, let's say. Yeah. For GPU jobs, we already discussed how to that these resource specifications, so this S-batch stuff on top, also can be used for GPU stuff. So there are settings for that in Slurm. One important thing is if you specify the GPU, you automatically get a part of the system for it. So if you request one GPU, you get a set of CPUs and a set of memory automatically assigned to. This is how it's managed in our center. So you don't have to specify like, I want to have one core and one GPU and this amount of memory. You just give me one GPU and you get a set of cores with that and some memory. This amount of memory and CPU cores you get per GPU cannot be made larger by us. So if you send us a ticket and say like, yeah, I want to have one GPU, but on the host like 80 terabyte or gigabyte of memory, this does not work out. This is like a hard split. We don't do that. It's part of Slurm.
If you need that, you would have to allocate 2 GPUs or whatever.
Yeah, or the whole node,
Yes.
and then use one GPU and the memory and so on. Yeah.
Not recommended.
Yeah, of course, not recommended. Yeah, you are accounted for all 4 or all 8 GPUs while only using one. And also it might be that we see it in the cluster monitoring that you requested a whole node, like a whole Alex node with 8 GPUs, but use only one. It might be that you get an email from us telling like, what are you doing with the other 7? You're wasting resources right now. Of course, you can still argue with us, yeah, and we probably accept it, yeah, but it is like, yeah, we see that as a more suspicious way of computing, wasting resources. So that's why we probably write a mail. You still have to use n tasks and CPU per task. So n task is 1 in most cases. So Slurm assumes n tasks like equals 1 if you don't set anything. So if you want to do like MPI where only the master is using the GPU, yeah, you have to specify with minus n tasks the number of MPI processes you want. And then 1 uses the GPU under the hood and so on. With sinfo, you can get all the available partitions, of course, on the systems. And then how do you request a GPU? In the easy cases, it's this minus gres equals GPU, and then the count you want, how many GPUs you want. This means that the type is not important. I just want to have a GPU, yeah, or 2. And normally this is applied for the ones we have a work or any partition. So you get assigned to that partition and get something out of that. If you want to have a specific GPU type, you have to use this gres equal GPU colon, the type colon, and then the count, like A100 colon 4 gives you 4 A100s. And in some cases, so especially on Alex, you need to specify a constraint if you want to have the 80 gigabyte version of the A100. So there are special versions out of that. They are all managed in the A100 partition, so there is no differentiation in the partition, but we have a constraint, so minus capital C, and then this A108 underscore 80 gives you access to those. Yeah, only on Alex. Unfortunately, on tiny GPU, you have to specify the type and the partition. So here is an example. We want to have one V100, so we also have to specify the partition V100. Same like if you want an A100, you have to specify A100 in the front and PUA100 in the end. Okay, so here's a example file for GPU jobs. Again, bash minus L on top, of course, and then the gres, and we get one A40 GPU in our job. Yeah, on Alex, you get with one A40 GPU, you get 16 CPU cores. That's what we have specified here. So this means that we want to have an MPI application with 16 MPI processes and one A40 GPU. So probably one of the MPI processes managing the GPU or something like that. One thing that came up more often in the support tickets is how do I test my batch scripts? So this is a common problem. You wrote a batch script and either you fire it up on the cluster and it fails quite fast, or you are really good at writing shell scripts and you made it right in the first time. If you don't want to do that, you can test your scripts inside of an interactive job. So you get an interactive job there. How you can do that is described in our documentation. But basically what you need in the first thing is you need all the SBatch lines that are defined in your shell script. So the resource specification, you want to have the same resource specification in the interactive job as in the compute job that you fire up later. So with that, we get all the SBatch lines and print the output, all the options in one line for easy copying. And then we apply the salloc command. We copy and paste the options from above and set a short runtime. Since this is the last option, it will always override if there's a time in here. Doesn't matter, just there's a small time here. So you have a job for 30 minutes and then source the script on the compute node. Do not execute it like / and your script, but source it, because sourcing means you're staying inside the shell you're currently in. If you do an execution, it will open a subshell and you don't want that. You want to stay in the current shell you are. That's why using source. Okay. And some minor important topics, let's say. So we do monitoring of our cluster systems. So we use Cluster Cockpit for that. That's developed in-house. And you can look at your jobs either by going to monitoring.nhr.fau.de or taking the button in the cluster in the HPC portal. There's a button in your user page where you can jump over to Cluster Cockpit to look at your own jobs and so on. If you want to do own measurements that are using these resources that we use for Cluster Cockpit, you can do that. So examples are PAPI, VTune, or Liquid. Liquid is also developed in-house here. You can use it with -C, HWPerf. This disables basically the monitoring, hardware monitoring. There's still data available in the cluster cockpit, but not from the hardware itself. Like you get like the memory consumptions and so on. That's software stuff that can be retrieved, but like the flops rate and memory bandwidth and so on, that's hardware data. And this will be turned off just for your job. And as soon as your job finishes, it fires up again and you get the data back. But if you, this is only important if you want to do own measurements using like PAPI or VTune or Liquid. For some clusters with shared nodes, so the tiny GPU and Woody and so on, this -C HWPerf only works if you have a node exclusive job. Of course, if you're sharing the node with other users, we cannot give you access to these hardware counters because then you can read stuff from the others. And we do not allow that, of course, for data security reasons, because you can imply back what is the application the other one runs on the different core, basically, by looking at the hardware performance data. You do not want that. So that's only allowed if you use the exclusive job. So SBatch -- exclusive on Woody and Tiny would do that for you. What if my workflow takes longer than 24 hours? This is a quite common topic. So all our systems have a maximum job runtime of 24 hours, period. Yeah. If you have issues with that, contact us. Yeah. We are happy to help. And it's probably an advice from our side. So it will involve some work on your side, like adding like checkpointing restart, or change jobs or something like that. So it might be minor changes in your shell script or bigger code changes in your application. Yeah, it really depends on the application you run on. It can also be part of code optimization and parallelization. So if we can tell you, yeah, if you write this algorithm like that, then you will be finished in 24 hours and don't take 3 days. So it might require some work on your side. But also it might be that we do something to make it work if it's some exceptional case.
There's a question from the chat.
Yep.
Can I use Cluster Cockpit for monitoring Intel GPUs?
No. There are 2 points. First, we do not operate Intel GPUs. And second, we use Liquid under the hood for getting the monitoring data. And Liquid does not support Intel GPUs.
Not yet.
Yet. Yeah. So at some point, yes, but since we do not operate Intel GPUs from our side, you cannot see anything in Cluster Cockpit. LRZ is operating Intel GPUs, but as far as I know, they don't use Cluster Cockpit. Another thing, or last thing from my side, unfortunately, this thing here on top is really annoying. No, it's impossible. Okay. So what is if my job doesn't start, and maybe for a little longer than like 1-2 minutes? You can look at the reason for it, why it did not start, by typing SQ. So SQ has a node list in brackets reason column, and there it tells you why it is like that. So the first 4 ones are the basic ones. Priority, so some higher priority jobs have to be scheduled first before you can run again. Dependency, you have specified dependencies, job dependencies. So this job has to wait until the other one has finished. For example, then of course it will not be scheduled, and the reason will be, yeah, I have to wait. Resources, if some resources are simply not available that you need in your job, not enough nodes free and stuff like that. Requested node not available is somewhat special because it means that Slurm scheduled the job for a specific node and then it got unresponsive. So it's at the moment not available.
Could it also be that you requested a specific node and it's just blocked by something?
Yeah, that is the same thing. Yeah. And in that case, it might even be that you have to cancel your job and restart it simply because this node is not available at the moment. And it might not be available for the next 2 weeks. So you don't want to wait for 2 weeks until the node is booted up again, because Slurm keeps this configuration. Yeah. So the thing is, just cancel it and resubmit it, and then Slurm will select different nodes and it will probably run. There are other limits that are more related to groups. So most of you are in projects, and these projects are seen as a group for us. Or association. So if you have this association group resources limit, this means like the resources for the whole group are currently in use. So if you have like a group limit of 16 GPUs and all the 16 are currently used, and you get a job there, then you probably see this reason. A QAS group, same thing. So things that are specified for a specific quality of service agreement are currently all in use. And partition resource limit, all the assigned or the resources in the specified partition are currently in use. Important is this priority thing, depends on multiple parameters. It's not a thing that we set, and we reduce it for people we don't like. That's not the case. The priority is automatically calculated based on the waiting time. So if you waited a long time for a job, you get a higher priority so that it starts earlier. Depends on the partition you used, on the user group, so which group you're in, and recently used CPU time. So if you use a lot of jobs recently, then your priority gets reduced so that the other ones also can get their computation done. And this is called the fair share. Yeah, so just to be fair over everybody, if you run a lot of jobs, your priority get reduced. The ones who do not run any jobs, they get scheduled first. Okay, and then the last thing, or almost last thing from my side, how to monitor what's going on in your jobs. Yeah, so of course we have Cluster Cockpit, so you can see some basic metrics of your job. But you cannot really look inside it. Yeah. So what is currently executed, which binary is executed if you have multiple binaries in your job, where it is in the binary could also be an interesting information, which is not provided through Cluster Cockpit. And for that, you can attach yourself to the job. That's basically the command above here. So srun ---- job ID, then you specify the job ID which you want to connect to. You say overlap because you want to overlap the resources between the job already running and your shell you want to open. You want to use the same CPU cores and so on, otherwise it's completely useless. And this in the back just starts a shell, a login shell. For CPU jobs, you can use top, htop, or perf top if you have -c hw perf set. So perf is one of these hardware performance command tools. It will look basically where in the code you are currently in. So if you're waiting in a barrier, it will tell you you're in a barrier. It will use the function names of your binary. So you could basically check that out. For GPU jobs, NVIDIA SMI is the tool to go. And as I said, there's also Cluster Cockpit. And if you're interested more about that, there was a talk at the January HPC Café. Look it up. There's the clip, but there's also the slides linked on this page. What we have left out, or I have left out now, so if you're a tier 3 user, so all university personnel and so on, but need more computing power, you can request access to NHR and FAU resources. These are the two links. So one is for Alex and one is for Fritz. Of course, we do not allow everybody to go there. So we do some basic checks whether the jobs are running okay, because if you're still like a lot of optimization space left, then maybe you first optimize on the other system before we let you on the more powerful system. Yeah, and if you need multi-node GPU jobs on Alex, just write a mail and request it. We will also check like how your one single node job runs and so on, and give you some recommendations or something like that. Yep.
I have a generic question about job arrays. If I'm using
I'll
like
do that in a minute.
He's the man for job arrays.
For 5 minutes or so,
okay.
I cover that.
Yeah.
And then you can ask.
Okay.
Okay.
All right. So next topic, data staging. So there have been a lot of activities here in the HPC cafes that deal with how to deal with data on our file systems, because it's a prevalent problem, a real big problem that some people like slow down their own jobs or even everybody else's jobs by not dealing with data in the correct way. There have been 3 previous HPC cafes with that topic, 2022 and then early 24 and then just in October. And you can view all the videos and watch, look at the slides. There's also a specific section on staging, and this is what I'm going to cover briefly now. So what is the problem? You have a job that needs a lot of data, reading, maybe writing a lot of data. And the data is stored in a shared file system like Work or FastTemp. So these are file systems which are not your local SSD, right? It's not your laptop disk, which means everybody else, if you block this resource, it's a shared resource, everybody else will suffer. Not only you. You will slow down your machine, your code or your job, but everybody else will also feel it. So it's a good idea to be considerate. So the best kind of data access that file systems like is large files read or written sequentially. Okay, if you can manage that, if you can organize your data and your access to the data in this way, this is the best way you can treat them. And then it's pretty much impossible that a single user can do harm to everybody else like that. However, some access patterns are bad for performance and they might be required by your job. So for example, the main thing is frequent metadata access. What are metadata access? Everything that pertains not to the data itself, but to the bookkeeping information that's kept in the file system, like modification times, for example. So whenever you open and close a file, that's a metadata action. And this means if you have 1 million files that you need for your training or whatever, and then you read all those files, maybe multiple times, you open and close them in rapid succession in many, many subdirectories, maybe in one subdirectory with 10,000 files, which is also bad, then chances are that this will be a very slow thing, and you will also slow down the file system for everybody else who happens to be working there, because it all goes over the network, and something in the file system is busy keeping track of all these metadata operations. Parallel file systems like FastTemp, they are very fast, but they're only fast if you have the standard streaming sequential access to large chunks of data. And they're especially prone to those slowdowns if you do this very high frequency metadata accesses. This pertains to all the file systems, not just to FastTemp, but FastTemp is especially prone to it. So what do you do if you have the standard pattern of many files you have to work with within your job, but it's not strictly required to keep them as many files in the file system? You could do the following. You could pack them into an archive, like a zip file or a tar file. Keep them as a tar file. Typically, these files are big, many gigabytes probably, but that doesn't harm the file system per se. Now, what do you do if you want to access it? You start your job, and within the job, you read the tar file or the zip file, you unpack it on the compute node, which is typically equipped with a decently large SSD, local file system, and then you can work there. Two advantages: the local file system is not a network file system, so you're not using any operations over the network. You might still be stressing the SSD a lot, but it's only yours, okay, for the runtime of the job. So it will not interfere with other users' operations. And then, of course, it depends on what you want to do. If you need to modify those files, in the end, you need to copy the modified files back to the permanent storage, the shared file system, because every temporary file that you make on the compute node will be deleted at the end of your job. Or if you don't need to change anything, if you only need it for reading, for training, for example, you could just let it be or delete it at the end, and then nothing will be written. So here's a very simple example script, which could be part of your Slurm job script. What it does is it assumes that there's a zip file, an archive that happens to be, in this case, on Woody Home. And this is where all your tens of thousands of tiny files are stored. What you want to do is you want to unpack them into a local temporary directory on your compute node. There's a variable called tempdir, which points to the local temporary file system. And this mktemp command I'm showing here makes a subdirectory on tempdir with a unique name. Okay, so even if multiple of your jobs are running on the same node, this doesn't matter because it will be a unique file name. And the mktemp command will give you back the name of that file, actually the full path, and you can work with it, okay? And the second line here, you change this directory, you unzip whatever needs to be unzipped. So in this command, unzip, the file is read from the shared file system, in this case, Woody Home, and unpacked to the local temporary directory. And now you can work with it, okay? And it's only the whole load, the whole metadata load goes to the local disk. At the end, you can clean up. Here we're assuming that we're not going to be changing those files at all, but we can just delete it. So this is what this rm-rf worktier does. Okay. You can also just leave it be because at the end of the job, the temperature will be cleaned up automatically.
The question in the chat.
Yep.
Are my jobs slower if I launch them from home vault compared to launching them from home HPC?
If the data set that you want to operate on is on home HPC, you want to move it to home vault anyway. I think this is the answer we're looking for. Yeah? So home HPC is not a good place to store any data that you would need in this kind of pattern as input data. So any data that you can easily reproduce or load or download from somewhere else should be in like some large file system, home, Woody Home or work or whatever appropriate file system there is. For the home directory, there's actually, it's a high quality file system that has a lot of security. You have snapshots, you have backups, and this is not appropriate for stuff that you need during your job as a large input file. So do work on the vault or whatever it's appropriate.
Another question.
Another question?
How large is $tempdir on Fritz?
Fritz doesn't have local disks, but Fritz has RAM disks. Right? Tempdir is on a RAM disk. And I think, if I'm not mistaken, correct me if I'm wrong, the RAM disk can take up to half the RAM capacity of the node. It grows automatically. So it can be useful, of course. It's even faster than SSD, but the size is limited. So what are other options? So these were the simple cases, right? Stuff you have to unpack on the compute node. What are other options to work on large files? One very attractive option is HDF5. That's one of the possibility options you have to pack stuff into a large structure and use it as a kind of database, as a file system within the file. The advantage is that you open the file once and you can operate on the contents of the file without a lot of metadata operations. So that's a good idea. Much lower metadata load. The disadvantage is that code support is required. Okay, so your code has to support this kind of access pattern. It's not like opening a file and closing it again. You have to go through this interface. Another option is data streaming. We actually had an HPC Café about that early this year. So you could set up a kind of server within your job for direct data access. You can load the data from somewhere else, maybe somewhere in your institute or even from the internet if you really want. However, disadvantage is you may be limited by network bandwidth, of course. The bandwidth to the outside is not infinite. This has to be handled with care. Okay, so you can watch this HPC Café recording if you want. And the last option is to use a file system that is actually very fast and can deal better with metadata load, which is called workspaces. They're only available on Alex. I think on Fritz you can establish them, but they're actually made for Alex. So if you're not on Alex, you're out of luck. It's a high-performance temporary network storage. It's still a shared file system. And I guess it is possible to bring it to its knees if you really want, okay? But it can take a lot of more load than the others. There's documentation available if you're interested. All right, are there any questions about working with files and data?
How large my data should be if in order for me to worry about this?
You mean how small it?
How large?
Okay.
I start worrying about it, few GBs, few terabytes.
Well, if you have a few files with more than a few gigabytes that you just read or write, you don't have to care typically. If you have 10,000 files with only 10 kilobytes each, you might care. Of course, there's also ways to read 10,000 files sequentially, which doesn't have a lot of metadata load. If you don't do it once, for example, that's maybe not too bad. There's a gray area, of course.
I have to be more careful.
So usually you feel it. If you, for example, if you make a quick back of the envelope calculation. If you say, I can get something like 500 megabytes per second out of a shared NFS file system, and you know how much data you want to read in your job, and you see it doesn't take like 20 minutes as it should, but 3 hours, something fishy, okay? So make these rough calculations, see whether or not the data transfer is efficient. Of course, the time it takes to transfer data also depends on the current load of the file system. So you might just be unlucky, somebody else is using it right now with a bad pattern, and you're just somebody who suffers. That happens all the time.
What about the software installations? Is $home better option than $work?
If it's software that's easy to obtain and reinstall, I would always put it on work. Yeah. Because $home, as I said, is a high quality file system. It's for stuff that you don't want to lose. If it's a piece of software, you can just download and build again, do it on work. One thing that bugs many people is the question, I have a lot of jobs that are very similar, maybe a long sequence of jobs, or maybe 1,000 jobs that run the same binary with different parameters, some kind of throughput workload, or a very long chain of jobs. Now, it happens that Slurm supports this kind of workflow, and there's a couple of facilities you might not know about. So the first thing that's interesting in this respect is array jobs. Array jobs is for patterns where you have a lot of jobs with the same pattern. You might have a job that's parameterized by some number running from 1 to n, whatever. And you just want to run the same binary again and again, one per job, but you want to automate that process. So how do you do that? Slurm helps you with that. You can just submit your job with -- array equals, for example, 1 to 10. That's just an example. So I put it here with 1 to 5. The same is pretty much, the rest is pretty much the same as we showed before. Now, how do you use that? Once you submit this job, it's not one job that will appear in SQ, but in this case, 5 jobs. The job ID will be your normal job ID, and then with underscore, an index added that distinguishes one array job from the next. You can access this array task ID, as it's called, from the job script. Okay, so Slurm array task ID. This is the number in this case, which goes from 1 to 5. You can use it in whichever way you want. You don't have to use it. But for example, you could use it as an input to your own program, okay, if you need that, so that each instance of a.out knows that it's number 35. And then it does whatever is necessary for job number 35. Keep in mind that if you do it like that, all these jobs that you submit are eligible right away. So there's no implicit dependency. If the resources are available and if you're allowed to do so, they could all run concurrently. Okay. However, you might have that pattern, but it might be that one job can only start after the previous job has ended. Okay, maybe there's a checkpoint restart pattern, or you need to take up a computation with another task. For example, some kind of pre-processing, compute and post-processing work chain. How do you do that? How do you tell Slurm that one job depends on another job? This is what job dependencies are for. Okay, so you have sequences of jobs that depend on each other. Slurm supports that. And it's very simple. With sbatch, you can use the -d, or I think -- dependency option. There's a type, a colon, and a job ID. This is the minimal set of arguments that -d requires. The type is one of these 5. I'll come to that in a second. And the job ID is the job on which you make it dependent on. Okay, for example, a previous job that has to end before the current one can be scheduled. There could also be multiple job IDs here. Now, what are the available types? The usual type that you probably should start with is after any. after any means that this job that you just submitted can only start execution, begin execution after the specified job has terminated. And in this case, we don't care whether it has terminated okay or whether it has an error. Okay? If you only want to schedule the follow-up job if the previous job was okay, so exited with an exit status of 0, you can do that too. You say after okay. After okay means the job can only begin if the previous job has ended with a successful exit code, like 0 in Unix terminology. So these are probably the two most popular ones. There's one that we just discovered today, very interesting, singleton. If you have a real large bag of jobs and you don't really care which one of them takes longer or not, which one of them finishes earlier or later, but you want to know when the last one of these many jobs has ended, you can submit the job as a singleton. And a singleton means, so you use it as a type here, it means that this job that you just submitted can only begin execution if all other jobs previously launched with the same job name and the same user have finished. Okay, so you submit a large number of jobs, same job name, same user. They all do different things, different lengths, different runtimes. You don't care. They all can run concurrently or one after another. You don't care. But once the last one of these big bag of jobs has ended, your job will start. And then you can, for example, either do a cleanup, you can fuse files together or send an email, I'm finished. It's nice, I think. Here's a simple example about job dependencies. And I put together a contrived example here to keep it simple, a script-generated dependency chain. Okay, so we submit one job, that's our anchor, so to speak. We obtain from the sbatch command the job ID, which is done with this grep and cut combination, and we assign it to this ID variable. So ID now holds the job ID of the just submitted job. And then we have a loop that runs 6 iterations, from 1 to 6. And in this loop, we submit 6 more jobs with sbatch. And we use the dependency parameter after OK $ID, which means we are assuming or we only scheduling the job if the previous one ended without errors. And this is the ID we just calculated. And of course, the outcome of this sbatch command is a new job ID that we use in the next iteration. Okay, that way you set up an automatic dependency chain, and the way it looks like if you execute SQ is the following. This is my first job. Okay, 099. It's running right now. Since state R, I snipped the part of the line to keep it on the slide. So it's running on a node. This is the sign that it's running, and all the others cannot run because they are blocked by dependency. This is one of the job states that Tom explained earlier. Okay. And then once this job has ended, the next one will be eligible, and then it will start whenever the resources become available. All right, now, this is how you set up a chain of jobs with dependencies from the start. If you know the dependencies, you know how long this will be, then this is the way to go. There's another pattern you could follow, and this is what we call chain jobs. Chain jobs means that you submit the next job from the job script of the current job automatically. And that way you don't have to set up this loop that produces all these tens, hundreds, thousands of jobs, but you could have a chain of thousands of jobs that runs for weeks and always have just one job waiting in the queue. Okay, that might be attractive for some workflows. Now, how do you do that? You have a normal job script. I've omitted all the headers and the stuff. So you do your job, you do your work here, a.out. And then you want to submit the next job in the chain because it depends on the output of the current job. How do you do that? First of all, we want to make sure that if anything went wrong, we don't want to submit anything new because the chain should stop. If your job only ran for 5 seconds, chances are something went wrong. Okay, maybe the quota was full or something else crashed. So we want to make sure that the runtime of the job was at least, let's say, an hour. Okay, that's of course dependent on your needs. Here we choose an hour. So if $seconds is greater than 1 hour, $seconds is a shell variable in bash that tells you how long the current shell has been running already. Okay, and that means if your job has been running for longer than 1 hour, everything is fine. And then you want another condition. And this condition allows us to stop the chain whenever we want. If you see, for example, that your chain has been running for a couple of days and something went wrong, for example, your algorithm doesn't converge, or you see that you will be taking too long for this to make sense, you want to stop the chain. Of course, you could kill any job anytime just by looking at SQ and then do an S cancel, but it's much easier just to produce or to touch a file. In this case, I call it stop chain. And with that, if that file exists, that's the -E here, then the chain should be stopped. So the condition is the shell has been running for more than 1 hour, and there's no file called stop chain in the Slurm submit directory. If these two conditions are fulfilled, I go to the Slurm submit directory and I submit the next job in the chain. Of course, you could add a dependency here, depends on the specific use case. Usually, if you're at this point in your job script, whatever happened above is over. So you don't need a dependency, but of course, applications vary. Now, checkpointing is a technique that allows you to break this 24-hour barrier that Tom has mentioned. So we're quite adamant about keeping this limit. So what do? If you really need more than 24 hours, you have to convince your job to checkpoint all its data to the file system, hopefully a fast file system, and then to have the next job in the chain take up from there. How do you do that? Now, it's very similar to the previous setup where we have the chain job, but now we deal with this checkpointing. Of course, the particular way you do this can vary, okay? Depends on your application. I'm assuming here that your binary is a.out, and it can read and write checkpoints as given by this checkpoint command line option. My checkpoint is stored in fasttemp/checkpoint.dat. So everything is fine, a.out runs, it writes a checkpoint, and then I want to make sure that the checkpoint exists and it has more than 0 bytes of size. That's an indication that everything went okay. And still I want to be able to stop the chain, and I do not want a new job to start when the current script runs for less than an hour. Okay, so these are my 3 conditions now. -S now means file exists and has non-zero size. So you can be very sophisticated with this if construct here. You can add, of course, any other options that you deem necessary.
Is there a slash missing after that checkpoint?
Oh, yes, there's a backslash missing. I'm sorry. Yes, we will correct that. There's a question in the chat.
Is stop chain developed by user? If yes, have you any template for it?
Stop chain is a file that you can just generate by touch. So it can have 0 size. It's just the name that stops the chain, okay? So the chain stops as soon as this file exists. It doesn't have any content. So touch is sufficient to stop the chain. All right, and finally, some advanced user scenario. If you have a kind of throughput workload, like capacity computing, thousands of runs of a single binary, everyone maybe just a couple of minutes, but you still want to make use of the cluster resources, a very common pattern. Now you could submit all these thousands of jobs to the batch system and have the batch system deal with it. Okay, that's one option, but then the batch system has to deal all of thousands of jobs, and some people might not be happy about that. You can actually use Slurm to manage your job queue for you. So the scenario is, let's allocate 1 node or 2 of the cluster that will be on Maggie, for example, 20 or 40 cores, and let's run 1,000 jobs, serial jobs on these 40 cores. So whenever a new core becomes available, whenever it's bored, the next serial run starts. Okay, so it's like an automatic job queue that is managed by Slurm. This is possible, bag of serial tasks, and here's how you do it. In this case, we allocated 2 nodes. CPUs per task equals 1, specifies that every time I call srun, I actually only want 1 process because my basic workload is serial. And then this is my bag of tasks, 2,000 tasks. srun starts my binary, a.out. I'm using 1 node, 1 process on 1 node, so dash uppercase n1, dash lowercase n1. This mem per CPU 2 gig is necessary because by default, Slurm assumes that your job will use all the available memory on the node. So on Fritz, this will mean 256 gigabytes. That's a little bit too much, and also it will lead to the effect that no 2 sruns can run concurrently. So here we're making a reasonable estimate, like 2 gigabytes, and this way, for example, on Fritz, 72 sruns will be able to run concurrently. This is why we need this mem per CPU option. --exact specifies that we do not want to oversubscribe the memory per node. So exact means really obey this specification of mem per CPU. And the ampersand at the end actually makes sure that the srun is something like a task that is put into a big queue. And then what happens, all these 2000 tasks are put into the queue, and Slurm will work through the queue for you, not necessarily in order. So we checked that. We didn't find an option to actually specify the order. So the order in which these binaries are run can be totally random. Okay, but it will never, if you do it like that, it will never run more concurrent A.outs than are available cores on your nodes. So in Maggie, this will be, in this case, 40. Okay, in the end, we have a wait command. This is very important. Wait waits for all background jobs that are running in the current shell. If you omit the wait, then the loop will run, 2000 sruns will be queued, and the script will terminate, and that's it for your job. And for all the other 2000 binaries you wanted to start. So don't forget the wait. Any questions here? There are things like Jobber and GNU Parallel, which do similar things, but we try to do it with Slurm, and for this simple pattern, it works quite well. Yeah.
So it will shoot out 2000 jobs at the same time?
It will only be one job, but it will be 2000 job steps that are queued into a big queue. Let's say you have 40 cores on those two nodes, and then it will just work on these job steps. Whenever a core becomes available, whenever one of these binaries terminates, it will run the next binary and so on. It's like a big queue.
Instead of this, I did something like the job arrays, but you can say 1 to 100 and %10. Out of the 100, only 10 will run at the same time.
Oh, that's good. I didn't know that.
Yeah.
Good point. That's similar. Yes.
Okay.
But this, if you do it like that, the load will be automatically balanced. I don't know. We'd have to check whether this works with the array feature, but we'll try. Yeah, good point.
That's interesting.
But at least you get like 1000 divided by 10 jobs in Slurm. With this.
The %10 will is the number of jobs which will run at the same time.
But
So
Okay.
it will shoot 10 jobs at the time and then wait for one to finish to shoot the
Another one. Okay.
Yes.
Okay. Yeah.
So,
Yeah, we have to check that.
yeah, good point. All right, then let's.
Just one comment. When you do this on a cluster with a lot of CPU cores, make sure your access pattern to the storage is not harmful, because we had cases where people did exactly that on Fritz and killed our storage because they had suddenly 200 and more tasks accessing storage in a harmful way, and this is.
Honestly, Fritz is not the target machine for this kind of pattern.
Yeah, but if you allocate 2 nodes, it's only possible in a parallel cluster, so it can only be made in Fritz.
Yeah, you could do it on Maggie.
We tried it out on Fritz, that's why.
Yeah.
Yeah.
But you're basically right. Yeah. Any more comments or questions? No, because then we wrap it up. Thanks a lot. Hope you enjoyed the HPC Café. Bye-bye. Thank you.